Let's look at a concept called mutual inductance. Suppose we pass some current through an inductor. This would produce some magnetic field in the inductor coil. If the current is a changing current, the magnetic field would also be changing. Now, if we bring another inductor closer to the first inductor, near enough that the magnetic field that is produced by this inductor actually can go through the second inductor as well, then this changing magnetic field is going to produce a voltage across the second coil, and this is called magnetic induction. So, in other words, a change in the current in the first coil produces a voltage in the second coil. The ratio of the voltage induced on the second coil and the rate of change of the current in the first coil is called the mutual inductance. So the mutual inductance is given by M here. One way to characterize coils which are very close to each other is by this idea of mutual inductance. Another way to characterize two coils close to each other is by the idea of transformers. If a sine voltage is applied to one of the coils, magnetic induction would result in a sine wave in the secondary coil as well. The ratio of the amplitudes of the sine waves is called the transformer ratio. Usually, transformers are a name given to two coils which are wound in such a way that they share their magnetic fields. That is, the same magnetic field goes through both the coils. For example, they may be wound on top of each other. Mutual inductors usually refer to coils where, though there is an overlap of the magnetic fields, not all the magnetic field of the first coil passes through the second coil. We can make different sensors based on mutual inductance. For example, here is one sensor where essentially the principle is that the secondary coil or the second coil comes close to the primary coil. If it comes closer, more of the magnetic field goes through this and more voltage is induced across the second coil. Here is another example where instead of bringing the coil closer, what we do is we use a ferrite core to change the amount of magnetic field that is coupled between the first and the second coils. Another example of a sensor based on mutual inductance would be this. Now this is a special example which we'll take a look in detail. This is also called a LVDT. Now here what happens is the magnetic field from this coil is induced to two secondary coils, and depending on the position of the core, the magnetic field is induced more on the first coil or more on the second coil, and we take a difference of the voltages induced on these two coils, and therefore this is also an example of a differential signal. We'll look at this in a little bit more detail in the next slide. A linear variable differential transformer, LVDT, is a sensor that uses mutual inductance to work. A schematic of an LVDT is shown here in this figure on the left. A practical embodiment of the sensor is more close to the figure that is shown on the right. An LVDT consists of three coils, 1, 2, and 3. The first coil is a primary coil in which a sinusoidal current is made to run using a source. The magnetic field induced by the current flows through the two secondary coils. The amount of magnetic flux passing through the two coils can be changed by moving this plunger up and down. When the plunger is near the first coil, more of the magnetic field passes through the first coil and a large signal is produced across it. It works similarly in the opposite direction as well. Also, these two coils are connected in such a way that the current through one coil passes in the negative direction through the other. So let's discuss the working of an LVDT in a little bit more detail. So the input of the LVDT is a sine wave. and the magnetic field that is generated by this sine voltage passing through what is called the primary coil is induced to two different secondary coils. Okay, so when you have your plunger is at this position, that is, it is inducing more of the magnetic field to the primary coil. What we have is there is a large voltage on the primary coil, while there is almost no voltage on the secondary coil. Okay, so there is almost no voltage on the secondary coil. But when this plunger is at this position, where almost all the magnetic field goes through this inductor and no magnetic field goes through that inductor, what we have is we have a large voltage induced on this inductor, while we have almost no voltage induced on this inductor. Now the output of your LVDT is given by the difference of these two signals. So when the plunger is kind of inducing equal amounts of magnetic fields to both the secondary coils, we have a voltage that is 0. When we have a voltage when we have most of the magnetic field being induced to the first coil, we have a very large voltage here. And when we have a voltage that is being induced, most of the voltage being induced to the second coil, then we have again a very large output here. Notice that the two outputs are of different signs but have the same amplitude, depending on whether it's towards coil 1 or whether it's towards coil 2. In other words, the output amplitude is an even function of the displacement as shown in the figure. It does not depend whether the displacement is positive or the displacement is negative. The output is always positive and the output amplitude is always positive, and it only depends on the magnitude of the displacement. Now, if we have an output amplitude that is always positive, whether the displacement is positive or negative, how are we going to differentiate between these two different displacement profiles? Because both these displacement profiles would give you the same output amplitude. This needs some kind of detection mechanism which uses more than just the output amplitude to figure out the displacement. And what we need is what is called phase sensitive detection. We will be looking at phase sensitive detection in one of the later lectures. Finally, let's think about electromagnetic flow sensing, which is also based on electromagnetism that we have been looking at. Just think of what happens when if a copper wire moves through a magnetic field. As the copper wire moves, cutting the lines of magnetic flux, a voltage is induced across the copper wire. The principle of electromagnetic flowmetry is very similar to this. Instead of copper wire, we have the movement of blood through a blood vessel. Now, the blood has a conductance which is similar to that of a saline. As blood moves through a magnetic field, a voltage is induced across the blood vessel, which is measured using the electrodes shown here. The voltage induced is proportional to the volume of the flow of blood, and it is given by the product of the magnetic field, the length between the electrodes, and the velocity of blood as shown in this equation. Of course, in practice, the measurements may deviate quite a lot from theory for many reasons, including, for example, non-uniform flow through the blood vessel, the presence of blood cells, and so on.